Welcome to Lecture 17, Part 3 for Chemistry 418. This is the third lecture on separations. The previous two lectures covered solvent extraction, ion exchange, volatility-based methods, and this lecture is going to focus on electrochemistry-based methods, looking at solvent systems that include molten salts and ionic liquids. Pyro processing is the electrochemical process used for separating uranium and actinides from spent nuclear fuel. It's also known as electrorefining or electrochemistry. The solvent that's used in electrorefining or pyro processing is generally a salt system. An example is a potassium chloride, sodium chloride system. One advantage of using the salt system is it avoids problems associated with aqueous chemistry. No hydrolysis and chemical instability due to radiation are eliminated through the use of these salts. Within pyro processing, separation is driven by the reduction of metal ions to the metallic state. And this is based upon the differences in free energy between the metal ions and the salt. So within a potassium chloride, sodium chloride system, the window is fairly large. So for instance, you can make uranium metal before one would make potassium metal or sodium metal. So the solvent system is useful. One would not be able to achieve this with water. The thermodynamic data is generally relatively easy to obtain or at hand. This is not completely true. There are some systems that are a little bit more complex, and research is ongoing in understanding some of the fundamental chemistry. The basic process of electrorefining or the pyro process is shown here, where one has some spent fuel. It's basically dissolved in some sort of reduction unit. You get some electrochemistry occurring where the metals can be transported from their cationic state to a metallic state. This separation can occur. The metallic state can be separated, put into a further reprocessing system, a further treatment system where they're purified, and then particularly for metals, uranium and other actinides as shown here can be used for fuel fabrication. And an outcome is shown here. This is the reduction of uranium. These are uranium products that are formed from a pyro process. Fundamentally, the process is driven by this sequential oxidation reduction. You can get cations transport through the salt and deposited on a cathode, so one could have an oxidation reduction process. And the deposition of these ions depends upon the redox potentials, so one can use this to tune systems for selective reduction of given metal ions. As we stated on the previous slide, reduction potentials can be exploited in electrochemical separations to achieve preferential isolation of given products in the nuclear fuel cycle. Example is shown here where differences in the potentials for the formation of metal ions shows that we can have groups of metal ions separated. The key with this and other separation systems is that there's gaps, so one can use this differences in the free energies to achieve separation. So for here, for instance, these monovalents and divalents, very difficult to form into the metal compared to other parts of the system. Everything all the way up from these group 1 and group 2 elements to molybdenum. By tuning the potential, one can achieve separations. These differences in free energies are notable for separating out the different metals, noble metals, shown here. The phase of zirconium to iron, actinides and rare earths, shown in this area, and then the group 1 and group 2 elements. There's also a route for achieving separations by looking at solubilities of chloride in a different systems, for instance, cadmium. And then you can almost think of this as a solvent extraction or liquid-liquid phase, except the liquid phases, one are molten salts and liquid cadmium. One looks at the solubility of different elements in cadmium. So one can use this as a way to exploit the differences in behavior for solubilities in cadmium and use this as almost a solvent extraction process. And a lot of this work can be reviewed if one evaluates the Integral Fast Reactor program, the IFR program. As we discussed previously, volatilities are also a route for separation, and this can be applied to the molten salt system. Here's an example of vapor pressure, of temperature versus vapor pressure for different chloride systems. As we see that they can break into a few groups, we have shown here for tellurium, zirconium, iron, molybdenum chlorides, relatively high volatility at low temperatures. So for instance, anything above 1 atmosphere would be relatively high volatility. These temperatures, you can get 1 atmosphere for these elements at temperatures of 600 degrees, 600 K or less. So these can be relatively easily separated. And then for the actinides, you tend to get uranium and neptunium together, plutonium with some of the tetravalent, with some of the trivalents, and then some of the lanthanides separated off into a different phase. So again, higher vapor pressures can be achieved for lower temperatures with some of the chloride systems, and this can be used for exploiting separations. There are a few different examples of molten salt or pyro processes that have been used and explored for treating spent nuclear fuel and recovery of uranium. Example of one shown here is the oxide type reduction, where oxide fuel is dispersed in a calcium chloride, calcium fluoride salt at 800 degrees. Calcium metal is added to the uranium salt. The uranium salt, the fluoride or the chloride, can be reduced to the metal. Calcium gets converted to the chloride or the fluoride. So this reduces the uranium salt to the metallic phase. Once reduced, the uranium metal can be removed from the salt phase by being dissolved into a second phase. It's called the receiver alloy. For example, an alloy of copper, magnesium, calcium can be produced. The uranium is dissolved into this phase. It exceeds the solubility limit in the receiver alloy and precipitates. So you have separation of the uranium as it's going from the oxide phase at the initial component, reduced to the metallic phase, goes into this receiver salt and precipitates out. Other elements, including plutonium, some other actinides, rare earths, noble metals, can accumulate in this receiver alloy, and they can be separated by distillation. Remember that from the receiver alloy, the uranium precipitates, so things that are soluble in the receiver alloy remain separated from the uranium. The group 1 and group 2 elements, along with any iodine and bromine, accumulate in the calcium chloride fluoride salt phase, and again are separated from the uranium metal. And in the case if an oxide was originally used, you would form calcium oxide in the reduction process, so a direct oxide reduction can also be used. And in this case, the calcium oxide would be electrolytically reduced to metal for reuse within the process and insertion at the initial point as the reductant for the uranium. Another example of a separation process based on electrochemistry is shown here, in which uranium trichloride is added to a potassium chloride, lithium chloride eutectic, heated to about 450 to 500 degrees. That's one of the issues with molten salts. One needs to be at molten conditions. The uranium is added as a metallic phase into metal baskets. Uranium gets oxidized at an anode to the trivalent state. And so you have a basket, oxidation occurs, and then the uranium travels, it gets reduced back to the metal at a cathode. the transuranics and fission products get oxidized. So uranium will travel out. You can reduce it back to the metal. The fission products can travel to a liquid cathium cathode and get deposited there. So one can achieve a separation of products with metallic fuel and again produce this uranium metal on the cathode. Plutonium metal can also be formed based on similar processes described for uranium metal. An example here is the direct oxide reduction, in which plutonium dioxide is added to a calcium metal, calcium chloride solution. This impure plutonium metal, we get a reduction of plutonium from the dioxide to the metallic state. We form calcium oxide. This calcium oxide can be recycled by treating the calcium oxide with chlorine gas, forming the calcium dichloride. Again, this can be then reintroduced into a system for producing more plutonium metal. This plutonium metal can be further treated by electrorefining. The metal can be added to a magnesia oxide cup in a calcium chloride, potassium chloride salt at elevated temperature, in this case at 800 degrees, well above the melting point of plutonium metal. This melted plutonium metal can then be oxidized to plutonium trichloride, which dissolves in the molten salt. It can then travel to the cathode, as was shown here. At the cathode, it's reformed into the metal. Since it's at temperatures above the melting point, it melts off the cathode into a collection area, and this can be used to produce a ring of pure plutonium metal. Again, this separation process is similar to what can be done for uranium from the oxide. An alternate to pyro processing is use of ionic liquids. Ionic liquids are ions that are liquid at room temperature or up to 100 degrees C conditions. They're composed of bulky, unsymmetrical organic cation and an organic or inorganic anion. There's a large range of possible pairs of ionic liquids, both cations and anions that can be used. They can be task-specific ionic liquids. Some trends within ionic liquids is that they have low vapor pressure. They're able to dissolve organic and inorganic compounds. They're conductive, and a large advantage is their electrochemical window, which is large enough for the reduction of actinides to metals. The properties of ionic liquids can be tuned for a number of applications, including high solubility of a certain species, increase of a reaction rate, electrochemical window, as shown, as we've already discussed, related to electrochemical deposition, and specific interactions with the metal ion. In other words, using an ionic liquid with a functional group that will enhance interactions with a given metal ion. Ionic liquids have been known for about 100 years, with the first example shown here. The initial work focused on chloroaluminate anion species. This was part of electroplating aluminum, and a number of detailed studies were performed and identified limitations of chloroaluminate, particularly moisture sensitivity. Newer ionic liquids have been evolved from these, and they have non-hydrolyzing or stable anions. Then these also include moisture-sensitive ionic liquids, and references are shown in this slide. An overview of potential ionic liquid anions and cations are shown here. As you can see, for the cations, they're bulky, organic-based compounds with the amine charge species. The anions can be relatively simple, straightforward inorganic compounds, or a little bit more elaborate anionic species. One can functionalize ionic liquids as shown here, taking a positively charged organic species, functionalizing it so that you have a area where metal ion complexation can occur. From the literature, one can see that there's 10 to the 18th possible ionic liquid combinations. It's an extremely large number and opens up the possibilities of task-specific ionic liquids, including group actinide separations. Ionic liquids have been proposed as part of the nuclear fuel cycle. Shown here, ionic liquids can replace traditional solvents in the Purex process. As we mentioned earlier, ionic liquids have low vapor pressure. One can throw the ligands, such as tributyl phosphate, into the ionic liquid, then use this as a means of achieving a separation where the solvent phase, the organic solvent phase, is the ionic liquid. And one can also extend this is that you can possibly recover metal ions from a separation that have ionic liquids through electrodeposition. This reference here shows a flow sheet that has been proposed for using ionic liquids that fundamentally is similar to the Purex process, but that also includes separations from the uranium and the plutonium using an ionic liquid. And there are a number of different conversion procedures that can be exploited with this system. As we stated in the previous slide, ionic liquids have been evolved a bit since their initial conception about 100 years ago. The initial haloaluminates are not stable to reduction of the lanthanides or actinides to the metallic state. So for work that's similar to molten salt systems, one would want to develop ionic liquids that have good moisture stability, good cathodic stability, and a large electrochemical window around the order of 6 volts that allow the reduction of the actinides and lanthanides. Some of the advantages that one would have using ionic liquids compared to the molten salts are listed here. The ionic liquids eliminate the corrosion resistance that is necessary for a high temperature molten salt system. They can operate at elevated temperatures, the ionic liquids, in other words, on the order of 100 degrees, but not the systems, not the temperatures that are necessary for the molten salt system. And the molten salts also produce caustic side reactions, whereas the ionic liquids, those are eliminated. There is some data in the literature on the electrochemistry of lanthanides and thorium in an ionic liquid, one that we're interested in investigating. In this system, the lanthanides have been reported to be reduced to the metallic state, and thorium was surmised to be reduced to the metallic state, but was oxidized by moisture in the liquid, and the journal is shown here. And this work does point out an important consideration, that the role of water is a central component in the chemistry of ionic liquids. Ionic liquids themselves are poor complexing ligands for the cation species, so if water is present, you wind up coordinating the water around the metal ion, therefore that the chemistry winds up really being dictated then by water. As we discussed earlier, there's a large multitude of ionic liquids that are available for study. At UNLV, we've selected the TFSI, the bis trifluoryl methyl methane sulfamide, as the anion for ionic liquid, which is shown here. This compound has been functionalized. You can read about this in the literature, and we've shown that it has a large potential window with gold, platinum, and glassy carbon electrodes, and this potential window is large enough for reduction of actinides and lanthanides. The full ionic liquid that we're using, it has the cation of the N-trimethyl N-butyl ammonium along with the TFSI, and is written as this compound shown here. An example of the large electrochemical window for the ionic liquids is shown here. This band is our oxygen and hydrogen evolution window for aqueous systems. So this shows the limitation of doing chemistry in water, which is one of the reasons that initially molten salts were chosen. Their electrochemical window is larger. And here's an example of the electrochemical window for the platinum, gold, and glassy carbon electrode with the RTIL that we're investigating. And as we see, compared to an aqueous system of 0.1 molar sulfuric acid, the electrochemical window is much larger. The large negative regime, as shown here, that's accessible, allows reduction of the metal ions, and as we see here, that the glassy carbon electrode is the best system. Again, we also note that the TFSI is a poor ligand, so we're going to be removed and allow the deposition of the metal on the electrode surface. An example of work that was done using uranium and studying electrochemical reduction of the compound is shown here. In this case, a uranium TFSI compound was produced using uranium-3. Uranium-3 complex was uranium triiodide. This is some glove box work. This synthesis is fairly straightforward. It's shown here where we have the uranium triiodide and tetrahydrofuran with some potassium TFSI ligand is added together under THF, where we get a potassium iodide product and the uranium TFSI compound. We add excess of the potassium ligand. This is stirred for 24 hours under inert atmosphere. As we see a color change, which is indicative of the formation of the uranium TFSI compound. And initially you get a precipitate of the potassium iodide in this system, so one can achieve a separation of this product from this product. And then you can isolate the solid of the uranium after the initial separation of the potassium salt by evaporating off the excess tetrahydrofuran. So then you have a product that can be added to the ionic liquid. As we see here, that this ligand being part of the ionic liquid system, we should have a very soluble uranium compound. This uranium TFSI, uranium-3 TFSI, was added to the ionic liquid. Negative potential was applied. The metal deposition on the gold electrode surface was then evaluated by SEM, EDS, and XRD. The SEM definitely showed the uranium deposition on the foil, and the XRD sample is shown, also showed that we had alpha phase uranium. That's a relatively low temperature formation of the metal. And the EDS data shows that we did not have any oxygen formed. Now with this system, again, we use uranium-3. Doing this with uranium-6 could be a little bit more difficult because you'll have the eel oxygen present. And here's an example of some direct dissolution of uranium, where U3O8, treated with ozone, goes from being a solid to a solution phase. We get a dissolution of the material. Then evaluation. We did UV vis spectroscopy, and here's some XAFS data where we see that we have, this is XAFS of the uranium. We see these two oxygens. These are the eel oxygens on uranyl. These are the coordinating oxygens from TFSI. So this shows that this reaction forms the oxidized UO2 in the TFSI solution, and that any chemistry at this point is done with uranium, the uranyl. One of the issues with the uranyl is that we have oxygen present on that molecule, so reduction of this molecule on an electrode, we've shown that it, under certain conditions, can form the uranium dioxide on the electrode surface. This concludes part 3 of lecture 9, where we discussed molten salt and ionic liquid separation systems. The final part 4 of lecture 9 will discuss some actinide specific separations.